Okay. Whoops. Okay. I have this on the board because I tried to do it once before and I didn't turn the phone to record like I thought I did. So what we're going to do here is I'm just going to leave it on the board. But I wanted to tell you what we're going to talk about. With interference, things, I'm going to add a little bit on the side here, I'll raise part of it. When waves interfere, what you have happening is, I'm going to do this over here. You have one sine wave here, and another sine wave underneath it. And if we have a crest meet a crest and a trough meet a trough, so when you add those up, guess what you get? Bigger crest and bigger troughs, right? And that makes sense. The crests add. And we just add them up as we go. So if you add, this is known as constructive interference. And constructive interference, you can think about this and say, all right, the wave itself is, I can push it around. So if I push this wave over one wavelength, and now I put it start it right here, it looks like the exact same wave, and when it adds up, it's the exact same way. So you have constructive interference. You don't know if the wave is dead on each other or it just got pushed over by one wavelength increments. So when the constructive interference happens, you know that the light itself, or the wave, is off by n lambda. In other words, if I have constructive interference between one wave or another, they could start at the same spot, or one could be in front or behind by one wave, in front or behind by two waves, in front or behind by three waves. I just know that where they're at when they add up, where this second one is, it can be pushed back or before, but the thing is, it's got to start at wavelength increments, at single wavelength increments. So, for constructive interference, and if you want to put it in terms of degrees, in a phase you may have heard, because you can think of these as cosine or sine with a phase on them, the phase would be 0 degrees, 360 degrees off, 720 degrees, dot, dot, dot. And that n up here can be equal to 0, 1, 2, and so forth and so on. Dot, 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 behind the clock. Alright? So, that's constructive. Let's look at destructive interference. Destructive interference. This occurs when you have a crest meeting a trough. Now, when crest meets a trough, when bad meets the good, when the positive one equals the negative one, you get 0 out from it. So when you add these up, you get nothing there. Because this peak meets a valley meets peak. So when all that happens, you get destructive interference. You get no output. So how much does this one underneath, is it pushed or pulled behind by to make that happen? Well, destructive interference occurs by half wavelength, increments of half wavelengths. So we can say n lambda over 2, where n equals 135. You're like, 135? Dot, dot, dot. Why is that? Well, it's got to be pushed 90 degrees. In terms of phase, you say, not 90, I'm sorry. 180 degrees, then one wavelength push ahead again would be 360 degrees, or one wave. So that would be 540 degrees, and so forth. So how do you go from half a wavelength to one wavelength more? Well, that's 3/2 of a wavelength, 1.5. How do you get one wavelength more? 2.5. That would be 5/2. It's all fraction stuff. Love fractions, right? I know MLA loves fractions. She's very good at it. Part of the time. Okay, so 1, 3, and 5 for the N for destructive interference because it's off by 180 degrees. 180 degrees out of phase. Okay? So if you can think of constructive, pushed or pulled by one wavelength from initial starting point, destructive, pushed or pulled by 180 degrees or half wavelength or multiples of it, this will help you understand what we're going to see, what Young saw with double slit interference. So you took a double slit, and the gap of that double slit may be, for light you need it to be, less than a millimeter, really, to really see it well. You can do it, but it's really hard to see. We're going to show that here in a little bit. But what you see is, we're going to take that distance D, you'll go with that the slit, the distance between the slits, say, a tenth of a millimeter, a few widths of a page or something like that. And we're going to take light coming into it. So as the light comes into it, it's going to form little bitty emitters, basically. They're going to start emitting waves like this, just like on a ripple tank. Like on ripples in a pond, you could say. Actually, you can use water ripple tanks for this sometimes to demonstrate it. Not that you'll see any of those in lab today or anything. But what I want you to do, just think of it is, as it travels, see it goes, what you'll show is a center pattern that's bright. There'll be a dark spot, then a bright, then dark, then bright. And each one of these bright ones gets less and less intense. There's less intensity there, less brightness the further away you go from darn center. Well, if you think of the center of it, since that's centered in between, these things, that's an isosceles triangle. The legs of the isosceles triangle are the same length. So basically the path is the same. That would be here, that's the zeroth order there. So at the center is sometimes known as the zeroth order term. Now let's look at the one up here. It's a little more interesting. Actually, for you Star Wars fans, it's a lot more interesting. I'll tell you why in just a minute. So now here, one goes pretty much straight to it, or a little bit of a bend. This one goes over, and you drop a perpendicular down, and you can see this in your book, and there's a gap here, this distance here. This is the path difference. This is the path difference. This path difference is going to be equal to an even number of wavelengths of the incoming wave for a bright fringe. I said m lambda, because that's what you got to have for constructive interference. Now this is the first one away from the zero. Now how many wavelengths is that? The first one away? Well, first one away would have to be one wavelength. So this gap here would be one wavelength of light. Now since it's one wavelength of light, that means in here, that's 0 is in the middle, n is going to be equal to 1 there. That, of course, is known as what? All right, let's geek out now, family. The first order. And, it is to be feared. Unless you're in the last movie, Kylo took it down. Well, it was a nice man. First order, though, it was decent. All right. A bunch of ships anyway. Now, of course, the second one would be the second order. They just had, I don't know, maybe they danced a lot. Maybe they dance fighting like in Jumanji or something. Who knows? All right. So, of course, zeroth order, first order, second order. Those are bright fringes. Now, say I drew these lines to this dark fringe. This would be the first order dark, second order dark. You just count them off there, even though n is 1 and 3 there. But really, the bright ones, what they pay attention to, because that's where you can get light at. Now, what's interesting is they go down in intensity as they go off. The dark ones, of course, would be half wavelength. These are single wavelength path difference increases as it goes off. And this is not something you could understand with the ray model of light. You couldn't understand it. But you can with waves. And think of waves as emitters and path difference. It works. Dang it, it works well in terms of waves. Okay? And if you want to find the position of this bright fringe here, we call that Y sub, the book calls it Y sub M here. And And they say y sub m is equal to m lambda L. L is the distance between from the view screen to the slit over D. Of course, D is the gap between the two slits. And you can see bright fringes, and you'll see orders of these things going off. Now, in reality, where our eyes see stuff, the intensity dies off pretty quickly, but you'll see gaps in it. Of course, the dark fringes, then, it makes sense geometrically that they're halfway between each bright fringe. That makes sense if you think about it. Now, to find intensity, you've got to use electric fields, and the electric field intensity of an electric field is always basically the magnet. It's basically the electric field squared. I should say magnitude. It's the electric field squared. And so what you have, that's what we see when we perceive light as intensity. And the equation, the book derives it a little bit, is basically 4 times the initial intensity, or basically assuming everything worked perfectly. Cosine squared, m is the order, d is the, of course, slit distance, lambda is the wavelength of light, L is the length here, and over lambda. That should be times the further away you are. Alright. Now, notice this wavelength dependent, how this works. So if you use red, that's kind of a big wavelength versus green, which is smaller wavelength. If it's bigger underneath, it's smaller up above. So if we look at this with green, we may see it better than we see with red, because green, if this is smaller, of course, the whole thing gets bigger. If the denominator is smaller, the whole thing in parentheses is going to get bigger there. All right? And so, I think that's it. Let's see if we can see this, actually. Let's see if we can see it. I'm going to get the lights. I have a laser, and I think I'm going to use the green one first. I tried the red one in the practice one, effectively, the practice one I did. I'll show you. This is basically, it's just laser diode module, a little 3-volt source, and so we had trouble earlier. That's the problem. If I would put them in the right way, one way, one the other. Whew. Now, what's funny, you see that green here versus this red. And I'll do the red here. The red looks fainter, but that's because our eyes perceive green a whole lot more than do red. Our eyes are much more sensitive to green than red. Of course, if you can understand green shades a lot easier, it helps evolutionarily. But we're going to do this in green here. And what I've got a sheet here that's got a bunch of different single slits and double slits on it. We're going to shine this through one of the double slits here on this far side, closer to here. And we're going to look at it. Now I'm going to go, and we'll turn the light off, and we'll go back, get a really long distance, get the row so we can hopefully make it spread apart. Hopefully you can see on the screen. We'll see what we can. Alright, so you guys can probably still hear me, because I'm on this Bluetooth thingy. And what I'm going to do is put it on the one that's really, let's see, there we go. There we go, I'll put it there at the bottom. What you should see is center. And you see there's it spreads the light out horizontally. Notice a vertical slit spreads the light out horizontally. But what's interesting is, in that spreading of the light out, there should be some slight dark splotches, like vertical lines, where it's not just all continuous. And if you could do real close, you can see it. It's hard for me to do both at the same time, of course, I'm the only one doing this. But it definitely spreads it out there. If I go to the ones up above, let's see here. It spreads it out, but you don't get that fine what we call graduation. Basically, you don't see it as much. It just kind of spreads it out, but you don't see the pattern between. You don't see here that you would get down here. Alright, maybe you can, maybe you can't see it. That's the way it works. We get the fraction gratings, you'll definitely go see that a whole lot better. All right. So that's Young's double slit.